Welcome viewers to the second segment of the second lecture for the online series of lectures for the course of Algebraic Topology 1. We begin this segment with a lemma concerning simply connected space, which is lemma 3. It states that in a simply connected space, X, any two paths having the same initial and final points are path homotopic. Okay. Alright, so here goes the proof of this lemma. Let alpha and beta be two paths in X from x0 to x1. If I want to draw it, then it looks like this. This is x0 and this is x1. 2 points in the simply connected topological space big X, and alpha and beta are two paths, both starting at x0 and ending at x1. Okay. So it is immediate that alpha star b bar, or the reverse of beta. So alpha star beta bar makes sense, right? Which is, this is a loop based at x0, right? So you go from x0 to x1 via alpha and then get back to x0 via beta bar, which is the reverse of beta. So this is the loop in X based at x0. Since X is simply connected, the class of alpha star beta bar is the class of the constant loop at x based at x0. Okay. It follows from the definition of simply connectedness of the topological space X. Okay. Now I take this class alpha star beta bar and take the product with the class of beta on both sides, right? Okay. So now by associativity, I can write it as alpha star beta bar star beta is equal to beta. This is what we can write using using theorem 1 from lecture 1. Okay, and also we can write this as this guy as beta bar is a path from x1 to x0, right? So it is going to be the class of E sub x1, right? The constant loop based at x1 starts at x1 and ends at x1 is equal to beta, which implies the class of alpha is the same as the class of beta, which means that alpha is path homotopic to beta, which is what we wanted to prove, right? QED. Good. Okay, now we come to the concept of pointed topological space. Let X be a topological space with a distinguished base point x0 in X. Such a topological space is called a pointed topological space. Okay, and is denoted by this pair x, x0. Okay, all right. Now suppose H sub x0 is a continuous map between these two topological spaces that carries the base point x0 of X, that carries the base point x0 of X to the point y0 of Y. That is, H sub x0 of x0 is going to be equal to y0. We write the map, we write this map as H sub x0 from x comma x0 to y comma y0. This is called a based map between these two pointed topological spaces. Okay, this is a map between two pointed topological spaces, big X comma x0 and big Y comma y0. Okay, now if f is a loop in X based at x0, okay, then one can see that this composite H sub x0 composed with F being a map from I to the topological space Y with, check that, H sub x0 composed with F at 0 by the definition of composition is H sub x0 at f of 0, right? And since f is a loop in X based at x0, right, f of 0 is simply x0. And we know that H of x0 at x0 is y0 from the definition of the based map H sub x0. So this is equal to y0. And we also see that this composite satisfies H sub x0 composed with F evaluated at 1 is going to be H sub x0 of f of 1, and we know that f is a loop in X based at x0, so f of 1 is simply x0, so which means that H sub x0 of x0 is again equal to y0, which tells us that indeed H sub x0 composed with F is a loop in Y based at y0. So the correspondence F, the loop in X based at x0, to H sub x0 composed with F, which is a loop in Y based at y0, gives rise to a map between the respective fundamental groups with reference to the base points x0 and y0 respectively. Okay, gives rise to a map from the fundamental group of X with reference to the base point x0 to the fundamental group of Y with reference to the base point y0. Now we define it formally. Okay, we define this correspondence. Definition: let H sub x0 is a based map between these two pointed topological spaces x comma x0 to y comma y0. Let H sub x0 be a continuous map define H sub x0 star from the fundamental group of X with reference to the base point x0 to the fundamental group of y with reference to the base point y0 be the equation. We define this induced map by the following equation. H sub x0 star acting on this class of this homotopic class of loops in big X based at x0 is equal to this class of loops based this class of loops in Y based at y0. Okay, we have seen that actually these guys are loops in Y based at y0, which we have already seen. This is our equation number 2. This map H sub x0 star is called the homomorphism induced by the continuous map H sub x0 relative to the base point x0 in X. Okay, so this is the induced homomorphism. Okay, so a couple of things concerning this induced map. First of all, this map H sub x0 star is well defined. This guy is well defined. This is because okay, so what was this map? This map is a map from the fundamental group of X with reference to the base point x0 to the fundamental group of Y with reference to the base point y0. Okay, because this is well defined, since if a path if F and F prime are homotopic in X, right, are path homotopic in X, and big F is a path homotopy between F and F prime, then using the key facts used in proving theorem 1 in lecture 1, we see that H sub x0 composed with big F is going to be a path homotopy between H sub x0 composed with F and H sub x0 composed with F prime in Y. Okay. So it is immediate that they are path homotopic in Y using the key facts there. Okay. So which means that this guy is well defined, right? This guy defined by this equation, right? H sub x0 star at acting at F is equal to the class H sub x0 composed with F. This definition makes sense, right? It's well defined. Okay, so this was one thing. Another thing is to check that it is indeed a homomorphism. Okay, let's check that it's indeed a homomorphism. So H sub x0 star acting on F star G, okay, where these are two classes of loops based at x0 in the topological space big X. Okay. So by the definition, so this is nothing but, you know, from the well-definedness of this product, we can write first of all it as this, right? And then from the definition of this map, we can write it as the class of H sub x0 composed with F star G, right? So by definition, H sub x0 star. And then, so we also it's from using the key facts again. Facts used to prove theorem 1 in lecture 1. Again, that tells us that this is nothing but the class of H sub x0 composed with F star H sub x0 composed with G. Again, by using the well-definedness of this product, we can write it as H sub x0 composed with F, the class star the class H sub x0 composed with G, which again, by using the definition of H sub x0 star, gives H sub x0 star acting on F star H sub x0 star acting on the class of G, right? So if we denote it as equation number 3, then 3 tells us that this induced map H sub x0 star from the fundamental group of big X with reference to the base point x0 to the fundamental group of Y with reference to the base point y0 is indeed a group homomorphism. Okay, since this is equal to this, right? This star is in Y and this star is in X. Okay, is a group homomorphism. Okay, now as the notation suggests, the induced homomorphism, this was the induced homomorphism. It depends not only the continuous map hx0 between these pointed topological spaces, it also depends on the base point. That's why we are attaching this x0 to the continuous map. Okay, so the induced group homomorphism does not only depend on this continuous map, but also depends on the chosen base point x0. Okay, so that is why we write it as h sub x0 star. Okay, so there are certain properties of this induced group homomorphism which are called functorial properties. To understand the name or the significance of the name of functorial properties, you need to know basics of category theory. So let me list the properties and let me prove it. If you go over our first lecture of the category theory lecture notes that we offered a year ago in BRAC University, you will be able to see why it's called functorial. Okay, so but for the moment I'm not going over the categorical background to explain how it to explain the significance of this name. For the moment, let me just write down the properties that this induced homomorphism enjoys. Okay, so let me write it here. The functorial properties of induced homomorphism. H sub x0 star. Okay, so it's given by the following theorem, which is theorem 4. If H sub x0 is a continuous map between these two pointed topological spaces, and K sub y0 is another continuous map between these two pointed topological spaces, if H sub x0 and K sub y0 are continuous maps between pointed topological spaces, so they are both based maps between respective pointed topological spaces. So these things need to hold. Y0 is equal to h sub x0 of x0, and z0 is going to be equal to k sub y0 of y0. That is, z0 is going to be equal to k sub y0 composed with h sub x0 at x0. Okay, so this is the story of the base points, of the concerned base points. So if this is the setup, then the induced homomorphism of this composed map k sub y0 composed with h sub x0 star, the induced homomorphism of this composite, okay, is given by the composition of the respective induced homomorphisms, like k sub y0 star composed with h sub x0 star. So this is the result. This is one result. This is one of the functorial properties. If I sub x0 is just the identity map between these two pointed topological spaces, which is of course continuous, is the identity map, no, I think I made a mistake here. It should be x, because we are talking about the identity map, right? So I sub x0 is the identity map from x comma x0 to itself. This is the identity map. Then, so it's a continuous map from x comma x0 to itself, from the pointed topological space x comma x0 to itself. Then the corresponding induced homomorphism I sub x0 star from the fundamental group of x with reference to the base point x0 to itself is just the identity group homomorphism, is the identity group homomorphism, right? So it means that if this guy acts on an element of this group, then it spits out the same element of the group. Nothing changes at all. This is the identity group homomorphism. Okay, so you see that if you think closely, you will see that, so this theorem tells us that things have been translated from the language of from the setup of topological spaces to the setup of groups. So this is what we mean by functorial. Functorial, functorial property, because this induced map takes things from the category of topological spaces to things in the category of groups. Okay, so you have the setup. We have things in the framework of topological spaces where things are connected to each other by means of continuous functions. Then you take everything to the framework of group where the objects there are talking to each other by means of a group homomorphism. So this is what you do by means of this functor. So this induced group homomorphism is acting like a functor between these two categories, the category of topological spaces on one side, the category of pointed topological spaces, to be more precise, because we are fixing the base point. Okay, so the category of pointed topological spaces is at one side, and the category of groups is on the other side. And the induced homomorphism is taking things from one side to the other side. Okay, so this is roughly what's happening. Okay, so now we need to prove this theorem. Let us go over the proof. Excuse me. Proof. So note that K sub y0 composed with H sub x0 is a continuous map from the pointed topological space x, x0 to the pointed topological space z, z0. Okay, why? Because the composition of two continuous maps is also a continuous map. Okay. Indeed, we gotta check that the base points, are transformed accordingly. Indeed, K sub y0 composed with H sub x0 from x, x0 to z, z0 as a map between pointed topological spaces yields z0 is equal to K sub y0 composed with H sub x0 acting on x0. Okay. Okay. So the induced homomorphism of this composite is going to be a group homomorphism between these two fundamental groups, okay, with K sub y0 composed with H sub x0 star acting on this group element, which is a loop in X based at x0, is by definition of this induced homomorphism equal to the class of K sub y0 composed with H sub x0 composed with F. Okay, this is from the definition of definition of induced homomorphism. Okay, and this holds for a given group element, right? In this group, pi 1 of x comma x0. So this is our equation number 4. Okay. On the other hand, since H sub x0 star is a map from pi 1 of x comma x0 to pi 1 of y comma y0, right? And K sub y0 star, this is the other induced homomorphism between fundamental groups. It's from pi 1 of y comma y0 to pi 1 of z comma z0, right? One has their composition as you know, K sub y0 star composed with H sub x0 star as a map from pi 1 of x comma x0 to pi 1 of z comma z0, right? With K sub y0 star composed with H sub x0 star, this composite of group homomorphisms acting on an element of this group. Okay, this is an element of this group, is by the definition of standard composition is K sub y0 star of H sub x0 star acting on this element of the group, right, is equal to, from the definition, again from the definition of this induced homomorphism, we can write it as this, as H sub, the class of H sub x0 composed with F, and then this induced homomorphism by again the by the definition of this induced homomorphism is going to be equal to K sub y0 composed with H sub x0 composed with F, the class of this guy. Okay, so this is equation number 5. Okay, using 4 and 5, one immediately sees that K sub y0 composed with H sub x0 star, right, is going to be equal to K sub y0 star composed with H sub x0 star. Okay, which is both of them being equal to this the composition of these three maps. Okay, this was one thing. Now for the identity map, I sub x0 between these two. So I sub x0 being the identity map from the pointed topological space to itself with I sub x0 of x equal to x for all x in the topological space X. The induced homomorphism I sub x0 star from the fundamental group of X with reference to the base point x0 to itself reads, I sub x0 star acting on a group element here, the class of F by the definition of induced homomorphism equal to I sub x0 composed with F, the class of I sub x0 composed with F for a given group element, right, in this fundamental group. Okay, so by the definition of the identity map on the pointed topological space, we know that this is simply F, right, the class of F. So it means that this guy is indeed the identity group homomorphism, the identity group homomorphism, which means that for the fundamental group, it acts on an element of the fundamental group and spits out the same element of the fundamental group, which is nothing but the identity group homomorphism. Okay, so that's it, QED. Alright, so at this point I'll take a break and then I'll be back with a corollary to Theorem 4. Thank you for attending this second segment of the second lecture.